we are going to talk about AI for fuzzing, a tale of two techniques. So, so I believe most of you are familiar with AI, but you are not familiar with fuzzing. So let me first do an introduction to what is fuzzing. So fuzzing is actually a technique to detect bugs in software. So so actually, there are many techniques to detect detect bugs in software. So imagine software is a patient, and we are using some analyzers to find bugs, and the analyzers are doctors, and the bugs are illness of the patient. So, so what we can do is we can scan the patient, so the patients don't need to act. So it's very fast because we don't need the patient to do anything, but it's less accurate because we just scan through everything. So correspondingly, in software bug detection, it is called static analysis. So we just scan through the source code or the binary code of the program and find bugs. And the other approach is we can observe the behavior of the patient. So what we can do is we can ask the patient to do something and observe the behavior of this patient to see if anything is wrong. So because this time the patient needs to do something, so it's called dynamic analysis. And fuzzing is a dynamic analysis technique. So so as I just introduced, fuzzing is a testing technique and is specialized for detecting security bugs. And it could be either black box, white box, or gray box. So the basic idea of fuzzing is to execute the target program with a large amount of randomly generated inputs. And because we are executing the program, we can observe for normal behaviors of the program, such as crashes. So if the program crashes, it means we found a bug. So because the inputs are generated randomly, so it's called, you can consider the inputs as fuzzy, so it's called fuzzing. The technique is called fuzzing. And the tool used for fuzzing is often called a fuzzer. So this is American Fuzzy Lob is actually a very famous open source tool, and it's named after a rabbit. So just now we know, okay, fuzzing is a testing technique, it's a dynamic technique for detecting bugs, and we need to execute the target program. And now let me introduce you what is gray box fuzzing. So as I just introduced, fuzzing can be categorized as black box, white box, and gray box. So for black box testing or black box fuzzing, it's highly scalable. So because we just treat the target program as a black box, we don't know what's happening inside. We just know what we put in as an input and what we get as output. So it is highly scalable because we don't need to analyze the program in detail, but it lacks effectiveness because we don't know what's happening inside the program. So it lacks effectiveness for testing. For white box technique, it is highly effective because we know every detail of the program during its execution. So because if you know how the program works, it's executed by the CPU instruction by instruction. So we track every detail of the execution. So we know what's happening inside the program. It's highly effective, but it lacks scalability. Because if we run white box testing on a very big program, we will run into trouble because there are too many program states for us to track. So it lacks scalability. So you may think, okay, black box is effective but lacks scalability, and white box is effective but lacks scalability. So you may think, okay, we can combine them together, but actually this doesn't exist. So what we can get is gray box. What we have is in between. So for white box technique, it's effective because we know what's happening inside the program. But actually for testing, we don't need to know every detail of the program. we only need to know the information that is needed for testing. So that's why we propose the idea of gray box fuzzing. So the idea is to collect what is needed and will only collect what is needed for testing. So it is effective, it is scalable, it is a jack of all trades, but it is a master of none. So but it doesn't matter it is a master of none, because this is where we can make improvements. So this is a meta model of gray box fuzzing. As you can see here, it works in 4 steps. So the first one is we generate test cases. We generate test cases for the target program. And then we execute the target program with the generated test cases. And after that, we analyze the execution feedback. And then what we can do here is, instead of terminate the whole process, we can use the feedback to adjust the test case generation to generate better test cases. So actually the step 3 and 4 differentiates the cutoff box for testing or fuzzing, because the more information we use, the more we are toward white box technique. The less information we use, the more we are towards black box technique. So this is a meta model so that's all about fuzzing and gray box fuzzing. So now let me introduce you AI for software analysis. So if you ask a security researcher or maybe a software engineering researcher, let's use AI technique to do software analysis, and mostly they will be like this. So they will say no, let's not use AI. But why? Because mostly the result of AI models are not explainable, so we don't know what's happening inside. And the other thing is, for most software analysis techniques, it requires high accuracy, because if we execute a program, most of the time the result is deterministic. So we need high accuracy for doing software analysis. So that's why mostly we don't use AI techniques for software analysis. However, we can also think about this problem in the other way. So where does AI perform well? So actually we are using AI models every day. So one example here is we are using face recognition to unlock our iPhones. So this is actually using some AI models behind. So in this scenario, why does AI perform well? It's because we can tolerate this scenario is tolerant to relatively low accuracy. Because if I cannot unlock my phone with the first glance of the AI model, then I just try it again, right? So we don't need that high that level of accuracy. So it's also fast, because it takes only 1 or 2 seconds for us to unlock the phone. So also we can retry it for many times if it doesn't work. So the 2 characteristics of the scenario here is it's tolerant to low accuracy and it's fast. It allows us to retry with the AI model. So this is where AI performs well. So this gives us hints of where we can combine AI and fuzzing technique. So because we need to find a scenario where we are tolerant to the relatively low accuracy, and we could execute very fast and retry with the AI models. So let's come back to the model of fuzzing to see where we can apply AI techniques. So for generating test cases, yes, we can do that. There's a technique called sample fuzz, and it is using some AI technique for us to generate test case. Because we are generating a large amount of test cases, we don't need that kind of accuracy. And for testing, the purpose is to generate unexpected input. Because when the programmers write the code, they are expecting some inputs. But if we want to find bugs, we need to come up with some inputs that is not expected by the developer to find the bug. So we can use AI to help us to generate the test cases. So for executing the target program with the generated test cases, the answer is also yes, because we can actually generate a large amount of inputs, and we need to select which input should we execute for testing. So the selection process could be done by AI techniques, because it doesn't require that high level of accuracy, because we can generate a large amount of inputs, and if the AI models somehow filters out very good test cases, it doesn't matter, because we still have a lot of other candidates. So for using the feedback and collecting the feedback, the answer is also yes, because analyzing the execution feedback is actually a very time-consuming task, and if we use AI model, we can speed up this process, and it doesn't require that accuracy again, because we are executing the target program with a large amount of test cases, and if this time we have a wrong result, it doesn't matter, because we can always come up with new test cases. So this is roughly where we can apply AI techniques with to fuzzing. So let's come to the details of each aspect. So first, AI for test case generation. So what we can do is we can use the AI model to learn the input format and generate new inputs with the models. So why we need to learn the input format? So the answer is, if we are trying to do testing, so the purpose of doing testing is to find unexpected inputs of the program. So let's say you have written a calculator program. I saw that most of you look very confused. So let me give you an example here. So let's say we are supposed to test a calculator program. So what is the expected input of the calculator program? It's some kind of formula or expressions, right? So it's like the expected input is 1 plus 1, or maybe 1 times 2. So, but what is the unexpected input? Maybe what we can do is we can put in some random characters, maybe some even Unicode Chinese characters. So this is unexpected by the developer. And how the program handles these unexpected test cases will affect, may have bugs. It's often, the bugs are often inside this kind of code. However, the programmers are very smart. They won't make such low-level errors. So what we do is we need to somehow they have write. Most of the programmers will write sanitization code for their program. They will sanitize the input before they reach the core logic of the program. For example, for the calculator program, the programmer the program may not accept any random input to process. The programmers can write sanitization code to sanitize the input. Let's say if the input has some random characters, it will be immediately rejected, and it will not reach deep into the deeper logic of the program. So in this case, we need to somehow generate a valid input so that the program can accept and process it. And yet it is still quite random so that we can find bugs. So that's why we need to use some kind of models to learn the format of the input to make it somehow valid. And the second one is AI for faster program execution. So because testing technique is a dynamic analysis technique, we need to execute the program every time we run a test. So the faster we can execute the program, and the more test cases we can try for a given time. So the core idea here for using AI model is we can use an AI model to learn the input reachability information. So to predict if a given input can help us to reach certain part of the program. So if the input cannot reach some interesting locations inside the program, then we just filter out. We just don't execute those inputs. So this is where AI can help us to for faster program execution. So the third one is what we discuss in detail here today. So it's AI for execution feedback usage. So a very important problem in testing is we need to learn the relation between the input, the input, the bytes inside the input, and the coverage. So this is like which part of the input is going to affect which part of the code. So this is the relation. So because why we need to do this is because the input space for a program is actually infinite. We can feed any input into any program. So, but we can't do that in reality because we need to focus on testing some interesting characteristics of the program. So that's why we need to learn the relation between the content of the input and the code. So this is where we need to what we can. So this is where AI can help. So AI can help us to learn this relation between the content of the input and the code coverage. So we have done a study to study some techniques, some existing testing techniques using AI techniques and some traditional techniques. So this is a code, the result of our study, and we can see that the two techniques in the blue box are the AI-aided techniques, and I think it's not very clear if you see only from the screen, but I will explain. So the result here is the two AI-aided or DL-based techniques does not significantly outperform the traditional techniques. So overall, this means that the current deep learning aided testing technique is not performing that well. So the second one is about the prediction accuracy. So because here for AI-aided feedback analysis, we are using some models to predict which part of the program is related to which part of the code. You can see that the accuracy of the DL-based fuzzer is not. The accuracy is quite high, but the recall is very low. So it's because most of because the data is imbalanced. Because if we, as I just said, the input space is infinite, and most of the input are rejected by the program by default. They cannot reach any part of the code inside the program. So most of the content are just blindly predicted as not able to cover a certain part of the code. So this is the problem of imbalanced data. And the third observation here is we found that some AI models, most of the AI models used by existing techniques have limited expressive capability. So the biggest problem here is because we are trying to predict whether the content of we are trying to predict the relation between the content of the input and the reachability of certain part of the code. So let's say if we are trying to predict whether a given string can reach line 3 here. So if the program starts with So if the program starts with, if the string starts with ABC, then we can reach line 3. If the program is written like this, the AI model, most of the AI models can work pretty well because the location of the magic string ABC is fixed at the start of the string. So in this case, AI models can work well. But however, if the program is in the current form, so it's like if ABC appears in the string, then we can reach line 3. In this case, most of the AI models cannot work well because the models used in the existing techniques are position dependent, and they lack expressiveness to predict position independent relations. So this is the last aspect. And as for future directions, we can work from 2 aspects. So the first one is from the funding aspect, because the coverage is very poor for the AI aided techniques. What we can do is we can combine with hybrid fuzzing technique, which is to use some symbolic execution techniques to help the testing process. And from the AI aspect, what we can do is we can try to balance the training data, because most of the inputs are not reachable for the certain part of the program. So you can try some training data balancing techniques. And the second thing we can do is we can try to develop more expressive models which are position independent. So that's all about today's talk, and thank you for coming. Do you have any questions?
Okay. I have a short question. Because you're talking about gray box, right?
Yeah.
Have you think about doing? You know, there's a thing called introspection. So you have a virtual machine. Then you actually can look at the process, what is running.
Oh, I see.
Yeah.
So actually for so
from that virtual machine, you can do you can roughly see what are the process. Let's say I'm Amazon. I have a tenant who run a virtual machine. So I can do introspection of the virtual machine running within itself. I'm not looking into malware analysis because malware is a kind of software. So it's a malware dynamic fuzzing to test out to see if I fuzz the VM, what kind of result I'm going to get through introspection.
Actually, using some emulators or virtual machines is a quite popular approach for collecting execution feedbacks in reverse fuzzing, actually. And because sometimes we don't have access to the source code, there are actually two types of approaches for us to collect execution feedback. The first one is, if we have source code, we can use program instrumentation techniques. We can instrument some code into the target program, into the existing source code to collect the feedback we need during the execution. And the second case is for where we don't have the source code, we only have the binary of the program. Then how we can collect? So what we can do is we can use a virtual machine in this case. Because with virtual machine we have control of everything. We know the CPU, we know every state of the program. So yeah, that's a valid point actually. Yeah.